So everything we've learned so far was more or less the picture of muscle physiology and muscle biomechanics as it stood in maybe about 1950. So back then, researchers did not really know what the microscopic structure was of muscle because they didn't have the tools to analyze it. But they knew that it had these force production capabilities. And as scientific equipment advanced, there started to be some debate and investigation into what was the microscopic structure of muscles. So if you take a little slice of a microscope or of a muscle and you put it under a microscope, it looks like this. And what you have here are little strands, little fibers of muscle. So for example, like running horizontally like this. This is one strand of muscle. And there's little cell nuclei out here, or actually these might be mitochondria. And something to notice is, and something that people in the 1930s, 40s, 50s did notice, was something that's very visible right here. Notice how there's this wave-like pattern on the muscle. If I zoom in, it becomes a little more apparent. The name for this is striation. It means like striped. And skeletal muscle is still sometimes called striated muscle for this reason. Now, as imaging technology became better, people started looking at what, so imagine trying to zoom in right on, like just right there. What would it look like? Well, it looks like this. So you've got this one, and you've got these like kind of string-like things with this very clear repeating structure, like this. So the question then becomes, what type of microscopic architecture would show up like this under a microscope and would give us the kind of properties that we see, the force length, force velocity properties? So a lot of different models got proposed, but the one that won out was developed by two completely different and unrelated people who both happened to be named Huxley. And they were the first to propose the following model. And let's remember way back from week 9, one of the big mysteries of muscle is how it produces force without changing its volume. You remember my experiment about flexing your biceps with your arm in a water tank. So hopefully we'll see how this model not only explains force length properties of muscle, but also the microscopic structure and this constant velocity or constant volume mystery. So Huxley's really proposed the following structure. Starting on these discs, really, maybe there's like a structure that goes out like this, like strands. Okay, and then so these are like little strings attached to like a big disc, and that big disc is right here. It's called the Z-band, in case you were wondering. And it was known at the time, and is still the case, that there was this protein called actin. And there's another protein floating around in muscle called myosin. And this hypothesis says that, okay, well, actin and myosin are interleaving. They like overlap with each other, kind of like if you are interleaving your fingers together. And there's going to be like a left-right symmetry here. Where, so now we had drawing on top of our image here, we had actin going off like this. Oops. And then we're going to have another disc on the other side over here. So let me draw that in. Another Z disc. And then another set of actin filaments coming off like this. And then the myosin is this protein in the middle. So let's see if I can draw that here. So then myosin is like, oops, I want that color, in the middle here. And maybe because of this band in the middle, they're like attached to each other somehow. There's one more protein floating around, and it's called titin. Now, I'm fudging the historical record a little bit here, but it turns out that our modern understanding of muscles depends on also knowing about this protein called titin. Now, the intuition with titin is that it's going to keep these myosin fibers sort of centered between these two, and maybe I should label them, between these two Z discs. This one. Sometimes also called Z bands, because when you look at a microscope image, it's like a band of a darker color here. But three-dimensionally, of course, we're looking at like a flat picture from above of like a tube. So this is all like a tube going like this. So there's like a physical disc right here that all this stuff is attached to. So this is just a bird's eye view of an actual disc. So anyways, there is a protein called titin, and it is attached to myosin here, kind of like a little, almost, you can think of it like a rubber band. It just kind of goes to here, and to here, and to here, and to here, and same on the other side. So you can kind of see how this would keep the myosin proteins centered inside between these two Z discs. Now, here's what happens, and I have some videos later that really show in detail what is going on at the smallest level. Because if you would zoom in and say on this part, there's this whole business with, and maybe you saw this in exercise physiology or intro to exercise science, you've got these myosin heads that kind of crawl along the actin filament. But I want to examine this level of analysis first before I throw that at you, because this is what explains the properties that we saw last week. Let me just label this titin, T-I-T-I-N. This titin, by the way, is where the passive stiffness of muscle comes from. So that passive force curve, this one, that comes from titin. Titin is like a little rubber band, and when it gets taut and taut like a rubber band and stretched out, that's where you get passive resistance from. And you could maybe imagine, just like a rubber band doesn't produce any tension when it's slack, right? If this muscle gets short enough, then the titin proteins here and here won't produce any tension at all. So that explains this part of the passive force length curve. That's great. Then let's think about the ability of myosin and actin to produce force. So what we'll see is that these myosin proteins have the ability to grab on and pull on actin like this. And so there's these little heads, and they grab onto the actin and they pull it together. So you could see how this whole unit, and by the way, this unit is called a sarcomere. This is one sarcomere. you could see how this whole thing would shorten as the myosin pulls these two ends together. Now, here's what's really interesting, and here's why this model is so smart. Suppose that, and let me see how well I can, let me just draw like one piece of this. Suppose the muscle is really long, right? We've like really stretched our muscle out. So what's going to happen? The sarcomere is going to be longer, of course, but the myosin will be the same length. So let me see if I can try and draw this to scale. Okay, perfect. So that works. Obviously, we'll be getting a lot of passive resistance here because the titin will be all the way stretched out like a taut rubber band. But given that we've said that the ability of a muscle to produce force comes from these little heads of proteins on the myosin grabbing onto the actin, well, these myosin heads out here can't grab onto anything because there's no actin. So you only get these ones out here grabbing on to actin. Same thing over here. There's going to be all these myosin heads that can't do anything. So when the muscle length is large, then our force production should go down. And you could see how the same should be true if the muscle length is short. So again, I'll just do one little combo here. So when these are really short, what should happen is at some point the myosin is actually it's going to like hit the end and kind of bunch up like this, right? So if the muscle gets really short, it's going to bunch up over here and not be able to produce any useful force. So again, the only myosin heads that can create force are the ones here, kind of in the useful overlap. And so you could see how there would be some like optimal amount of overlap, some optimal length of the sarcomere. And at that length, the actin and myosin should be able to interact to produce the maximum amount of force possible. And if it's too short or if it's too long, then you should get less force production. And that is exactly what we see. So right here is when we have the optimal amount of overlap between actin and myosin. Out here and out here is when we have no overlap at all, or the whole thing is bunched up and can't produce any force whatsoever. With our modern understanding of titin, we also understand where the passive properties come from. And we even have some intuitions why this curve might start going up from 0 at the optimal fiber length, because you might imagine that titin is sort of adapted to start stretching out beyond that optimal fiber length. So this is well, the name for this is the sliding filament theory, sliding filament model, because these are like filaments, like little strands, little strings of spaghetti that slide past each other, and the amount of overlap between those actin and myosin proteins dictates the amount of force that our muscle can produce. So this explains both what we see on microscopes and electron microscopes and the phenomena that we see in the lab, meaning the mechanical behavior of actual muscle